All right, so here we are on question 9. So this one is one of the harder questions on the homeworks that you'll have for this semester. It's very involved, but it's a great problem to practice with, because if you can do this problem start to finish, it does a lot of concepts, and it'll be able to, you shouldn't have any trouble with a two-dimensional problem if you fully understand this problem. Okay, so let's get started. We have a playground. It's on the rooftop of a city school. Probably not the best design, but the school is 5.3 meters above the street below. Then there is a vertical wall on that building whose height is 6.5. Okay, so what that means is that this height is 5.3, and this height here then would be the 6.5. Leaving this little extra height on top of 1.2. Okay. That's a railing that goes around the playground, obviously to keep everybody inside. The ball has fallen to the street below, and a passerby returns it by launching it or kicking it at an angle of 53 degrees. Okay. Above the horizontal. At a point D, which is 24 meters from the base of the building. Okay, so the 24 meters would get them to the beginning of the building. The ball takes 2.2 seconds to reach a point vertically above the wall. So here's the wall. Vertically above the wall means that the ball is now there. Okay, so the ball started down here. Ball gets up there, and that journey took 2.2 seconds. Okay, so a lot of information. Not your normal. It's not on center. It's not at its highest point. It's not landed. It's up here. We don't know where. It's above the 6.5, but not by. We don't know by how much. So let's tackle this one part at a time. What is the initial speed of the ball? What was the initial speed at which the ball was kicked? How hard did they kick the ball? Okay. Well, we know it's going to be two-dimensional, so let's start writing out our two-dimensional projectile motion equations or charts. Okay. And we'll start filling in what we know. The x distance that it traveled was 24 meters. The initial velocity, well, that's one of the things I would really like to know. I don't know for sure here. Final velocity at this point, I don't know, but I do know that these are going to be the same because the acceleration in the x direction for projectile motions is always 0. And the time to get there, okay, time to get there would be at 2.2 seconds. So we've got that part. On the y side, I know that the ball went up, but it's not at its max. It's above the 6.5, so I can't put anything for y. V initial, another thing I'd love to know. Don't know that off the top of my head. VF, I don't know either. It's in motion here, so I'm not sure there. But I do know the acceleration is 9.8. And I do know that the time is 2.2. Okay, so a lot of unknowns on this one. So let's see, what else do I have here? Well, I have 3 things on the x side. So maybe I can figure the initial velocity on the x component of it. For that, we don't care about VF. So if we don't care about VF, we'll go ahead and pick the equation that doesn't involve VF, which is the change in x is equal to VI times t plus 1/2 AT squared. Change in x was 24. Initial velocity is what we're looking for. T is going to be 2.2. And then plus 1/2 AT squared. The A is 0, so that remains 0. So looking at the initial velocity, all we have to do is take 24 and divide it by the 2.2. And this will get us a VI or a V initial in the X component of 10.9. So let me go ahead and put that over here, 10.9. Okay. So we've got part of it. The rest of it to figure out is a little bit tricky if you're looking at this problem for the first time, but we do have enough information to figure out the other part of the V initial. The other part of that, it was told we kicked it at 53 degrees. Okay, which means the ball was kicked. Let's go over here. Let's go up here. 53 degrees. It has an initial velocity in the X direction of 10.9. How much in the Y direction is the question. So we can actually use tangent to find that, because it is dealing with the adjacent and the opposite. So if we remember tangent, we have tan of the angle, 53, is equal to the opposite, which is our question mark, over the adjacent. Okay, the adjacent here is 10.9. So we multiply over to the other side. We do 10.9 times the tan of 53, and that gives us our VI in the Y to be 14.5. All right, so now we've got that added to our table, 14.5 meters per second and 10.9. So if I want to know what the initial speed of the ball was, I have both the components, so I can find the excuse me. I can find the magnitude of these. Okay, I can find the magnitude of the total vector. So I know that this is 14.5. Okay, let me add that in, and then for the hypotenuse, we'll use the Pythagorean theorem, the SOHCAHTOA of those two. So we'll do a square root of 10.9 squared plus 14.5 squared. Okay, and that would be the hypotenuse, and that is equal to 18.1 meters per second. So, what was the initial speed the ball was kicked? 18.1 meters per second. Okay. On to part B. What is the vertical distance above the wall in which the ball passes? Vertical distance above the wall. So here we want from here to here. That's our question. Okay, vertical distance above the wall. Well, if I knew change in Y, that would tell me the height change from here up to here. Okay, which is great, because if I know the distance from here up to here, I know that this height is 6.5, so whatever it is beyond that would be the height I'm looking for. So we need to find change in Y. We don't have VF, which means I'll have to use this equation again for the change in Y. So change in Y equals to VIT plus 1/2 AT squared. Okay, so change in Y is going to be equal to 14.5 times 2.2 plus 1/2 of a negative 9.8 times 2.2 squared. Okay, so let's plug that into our calculators. 14.5 times 2.2 plus 0.5 times a negative 9.8 times 2.2 squared. Okay, and we get a change in Y equal to 8.2 meters. Well, the 8.2 meters, we have to minus the 6.5 because the question says it wants the distance above the wall. Okay, so if this is 8.2 minus 6.5, that gives us 1.7. Okay, that's 1.7 meters. What is the, okay, so part C, the last part. What is the horizontal distance from the wall to the point on the roof where the ball lands? All right, so where is this length, x. The horizontal distance from the wall to the point on the roof where the ball lands. Okay, so looking at that one, we need a few more things here. But this is 8.2. So this is almost a separate problem. We've got these just about figured out. Where this is new components, the 2.2 no longer plays. It's going to take longer to get here. So what we need to do is we need to completely set up a new set of tables for this. Okay. So with this being done, let's see what we can solve here now. If we start a new x and a new y, change in x is now what I'm looking for, and all I want is from this point to this point. Okay, so I'll have change in x, velocities, accelerations, and time. I'm also going to plug in all of my y's because it is two-dimensional. This is what I'm looking for. And we go, okay, what else do we know? Okay, so you can pick the usuals. You know that there is no acceleration in the x because it's projectile motion. Whatever these velocities are, you know that they're going to be the same. The change in y, okay, that we can figure out because we know the height here. The height here is 8.2. Okay, and the height from this to the roof is going to be the 8.2 minus the 5.3. Okay, so 8.2 minus 5.3 will get us the height here, not the 6.5, because that's actually above the playground. Okay, so not the 6.5. But if we take our 8.2 and we minus 5.3, that means the ball will have to travel downward 2.9 meters in order to make contact with the roof. Okay, so we do have that. Initial velocity, we don't know. Final velocity, we don't know. But we do know the acceleration is 9.8. Ooh, we're looking pretty scarce here. 2 and 2. Okay, so we have to figure some other stuff out in order to make this work. When I hit something like this, I like to go back to a previous step, look to see if there's anything else I can grab out of it. You'll notice we didn't fill out the final velocities on this first part. So we might as well go ahead and do that. If the initial velocity is 10.9 and there's no acceleration, the final velocity also has to be 10.9. If the final velocity is 10.9 at this point, then that has to be where this problem begins. So the final velocity here turns into the initial velocity here, 10.9. And also, this has no acceleration, so this is also 10.9. Okay, so we've got a lot more steps here, but we've got our usual VI, VF, and acceleration. This doesn't give us any new information, no matter what equation we plug into. So we'll have to start with the y, and we'll have to get the time to come over here and to solve for the x. So we're going to have to deal more with the y. But we can use that same trick, that this initial velocity is this final velocity. So we have to figure out what this final velocity is. So we can use the first equation for that. VF is equal to VI plus AT. Our VF is what we're trying to find. We'll have 14.5 plus, or it's actually going to be on minus 9.8 times 2.2. Getting a little cramped in there for values. That's why I did say I would recommend starting a new page, because this does get a little bit tight. So let's see what that is. 14.5 minus 9.8 times 2.2. And we get, oh, I think I got an error on there. Hold on. No, that was right. We get a negative 7.06. Negative makes sense. The ball is falling at this stage. So that should be right, 7.06. So that means the initial velocity over here would be negative 7.06. Okay, so now I've got three things on the y I can try and solve for time. To solve for time without dealing with VF, it's this equation. The change in y is equal to VIT plus 1/2 AT squared. If I start plugging in, I will see I have another problem. I'm trying to solve for t, but I have a t and a t squared. Okay, to combine these, a t and a t squared, you're going to have to use the quadratic formula. If you want to use the quadratic formula, you go right ahead. Use the quadratic formula and you'll get two answers for t, and you'll have to pick which one it is. The reason you have two answers for t is because delta y hits this point twice. Okay? When it reaches here, it is at the exact same height as it is here. So in the y perspective, it doesn't understand which one you're looking for. So you get two answers. You would, of course, pick the later one at which it ends up down here. Okay? Another way of getting around this without the quadratic formula is to then solve for what you can't find to then solve for t. So it sounds a little bit strange, but we didn't care about VF before. Let's solve for VF. Let's now care about VF, because we can solve for that one without the quadratic. So to solve for VF without t, you would need VF squared is equal to VI squared plus 2a change in y. VF squared is what we're going to now look for. Okay. VI squared would be our negative 7.06 squared, plus we would have 2 times our acceleration, negative 9.8, times our change in y, which is also negative 2.9. So remember, all the negative signs are coming in. And then when we're all done, we're going to take a square root of that as well. So let me punch in. Let's see what we get on that. 7.06 squared plus 2 times a negative 9.8 times a negative 2.9. And that gives us a VF squared of 106.7. Okay, so take a square root of that, and we'll get an answer of VF is equal to 10.34. Okay, so now this still isn't quite correct, because you took a square root of something, which means that this value can be positive or negative if you squared it. You have to look back at the problem and go, is that final velocity positive or negative? The ball here continues to fall, which means it is speeding up in the negative direction. So it started with negative 7.06. So this must be a negative 10.34. Must be negative. Now we have this. Now we can solve for time. Okay, so that's avoiding the quadratic equation. Now that we can solve for time, that means we have VF is equal to VI plus AT and solve for time. Here we're going to have a negative 10.34 equals a negative 7.06 plus a negative 9.8. We're just all negatives today, times t. Okay, so when I do this one, we're going to have negative 10.34 plus this 7.06. Okay, because I'm going to plus it to the other side, which means we're still going to have a negative. Oops. Plug into my calculator, right? We'll have a negative 3.28, and then now I've gotten rid of this over to the other side. I have this negative 9.8 times t, so let's divide by a negative 9.8, and that'll get t by itself. And it'll also cancel out the negatives. So we get t by itself, which means the time it takes is 0.33 of a second. Okay, to come down there, which makes sense because this was 2.2 and it got it like 80% of the way. So very, very short time, 0.33 seconds. Move that over to this time, 0.33 seconds. And finally, we can now solve for the change in x because we have the time. So using this to solve for the change in x, it doesn't matter which equation you want to use because they're all valuable here, so that's fine. I'm going to go ahead and go change in x is equal to 1/2 VI plus VF times t. All right, so change in x is what we're looking for. If I take half of VI plus VF is the exact same thing, so I'm taking half of 2 times VI, so it's just VI. So it's 10.9 times our time of 0.33, and that will get us our change in x. Our change in x comes out to be 3.6 meters. All right, so finally, what is the horizontal distance? 3.6 meters. Okay, it is a long problem. It is very intense, but it has you do trig, it has you do Pythagorean, it has you do sine and cosine, it has you do two tables. You use all the equations that can be listed. You might even use a quadratic formula if you wanted. It's a very, very involved problem, but it's a very, very good problem for teaching and learning and making sure that you fully understand. So good luck on number 9.